Hello and welcome to the final lecture on our heat unit, which is about thermodynamics. Thermodynamics means the movement of heat from one body to another, and is the study of how heat can be controlled and used in order to make our lives much easier. This is just conservation of energy, said in a different way. So previously, before we knew that heat was a form of energy, we used to think it was a form of caloric fluid and could be transferred from one object to another freely. After realizing heat was a form of energy related to the kinetic energy of molecules and temperature, we realized that heat would have to follow conservation of energy, and therefore there can't be any sort of perpetual motion machine, which does work constantly and without fail for the rest of eternity. Because of conservation of energy, this just isn't going to work. The second law is that heat of itself never flows from a cold object to a hot object. And the third law of thermodynamics states that it's impossible to reach absolute zero in a finite number of steps. So, absolute zero, as we were talking about, was the temperature at which all motion of molecules, all kinetic energy of molecules would be frozen and equal zero. The way we found absolute zero in the first place is that we found that when you take any sample of gas and lower the temperature so that it takes up less space, according to the ideal gas law, when you lowered the temperature of the gas by 1 degree Celsius, no matter what the gas was, you would see that it would lose 1 over 273 uh, part of its volume. Therefore, you can make the assumption that if you were able to lower it by 273 degrees, it would have no volume left. Of course, this is an impossibility. You can't get to zero volume with objects that have volume in and of themselves, such as molecules. Conservation of energy can further be written as heat added to a system is equal to the increase in internal energy minus the external work done by the system. And it also states that air temperature rises as the kinetic energy of the molecules rise as heat is added or as pressure is increased. An example of this conservation of energy in meteorological ideals is the concept of a Chinook wind, which is something that happens on the East Coast, where you have warm, moist air, which is going up a hill or a mountain. As it goes up, it cools and becomes less dense. And because it becomes colder, it is able to condensate into liquid water, which rains down onto the forest or the mountain. Then, as it comes down again, it warms up as the pressure increases, but it doesn't have the moisture that it had before, and it's just a hot, dry wind instead of a hot, moist wind. Another example of heat in our atmosphere is temperature inversion, which happens when cool air is trapped from going higher when there's a layer of hot air in between it and the upper atmosphere. So, because there's this layer of hot air coming from the desert over Los Angeles, then the cool air that comes in from the ocean is only going to be able to go up until it reaches the layer of temperature inversion, until it reaches the layer of hot air. And then it won't be able to go up anymore because it's blocked by the high pressure from the high temperature inversion pocket. This means that instead of going off into the upper atmosphere, when you look at Los Angeles, the cool air is trapped below this layer of temperature inversion, and all of the pollution that is made by Los Angeles is trapped under the layer of temperature inversion and becomes a layer of smog under the hot air. Probably the most useful ideal that's come out of thermodynamics in the long run so far is the ideal of a heat engine, where heat flows out of a high temperature reservoir and into a low temperature one. Every heat engine gains heat from a reservoir of higher temperature, increases the engine's internal energy, converts some of this energy into mechanical work, which is what we want to use, what we hope to use in order to drive our cars or to power our power plants or anything like that, and expels the remaining energy as heat to some lower temperature reservoir, usually called a sink. For example, if you look at a gasoline engine, you will see gas vapors coming in the left side in this first diagram, causing it to adiabatically, meaning with no heat added, expand. And as this occurs, the piston pushes up against the adiabatically expanded gas, adding pressure until a spark plug in part C is ignited, which causes there to be uh, work done by the higher temperature, which goes off and causes there to be work done on the piston, which drives our car. After this occurs, the right-hand valve is released, and the gas fumes are diverted into a lower temperature reservoir, and the entire process starts again. So this is an example of a heat engine. It's one of our most important heat engines, the gasoline engine. It's what powers most of our cars. However, heat engines have a problem, which is that the ideal efficiency, which is the work done by on the heat engine divided by the energy put into the heat engine, is dependent on the heat of the reservoirs. So the temperature difference of the reservoirs divided by the temperature of the hot reservoir where the heat is coming from in Kelvin. This is why we want engines to run hot. We want there to be as big of a difference as in temperature as possible so there is a greater efficiency. However, there is no way to get 100% efficiency no matter how hot you make the engine. Also, in this vein, in natural processes, high quality energy tends to transform into lower quality energy. Order tends toward disorder, where disorder is quantified scientifically as a quantity called entropy. This increase in entropy, when looked at scientifically and looked at with values that we're not going to define in this class, is related to the second law of thermodynamics. And another version of the second law of thermodynamics is instead of saying that heat flows from hot to cold, it means that entropy is going to increase during any thermodynamic process. The net entropy in the universe is going to increase. This means that the farther along in the universe we go, the longer the universe lasts, the more disorder there is and the less useful energy there is to be had. Eventually, this is going to lead to a system where entropy is maximized and everything is at the same temperature. So if everything is at the same temperature, then that means that there can't be any flow of heat, which means that we can't do any work with heat engines anymore. As a measurement of disorder is also something that we can see easily when we talk about processes and times arrow, which means that as time goes forward, entropy has to increase, which means that if you drop a water bottle or a glass bottle onto the floor, it's going to shatter. And that's going to increase the entropy. That increases the disorder of the system. You're never going to see the opposite happen, where a bunch of broken pieces of glass spontaneously form an ordered glass bottle. Instead, in order to do that, you will have to introduce heat and make order out of disorder at the level of your glass bottle, while the entropy of the universe is still going to increase. As we finish our unit on heat, I want to provide a sort of cautionary tale or a cautionary optimism, I suppose. The modern world would not be able to exist, and industrialization would not have been able to happen without this knowledge of heat. In addition to creating engines which drive our cars, it is also responsible for the advent of quantum mechanics, which we're going to get to later. and which is one of the most important scientific discoveries of the 20th century. That said, with the advent of industrialization, we also saw pollution rise, global temperatures rise, and in the words of Nikola Tesla, man-made horrors beyond our comprehension come into being as a result of the physics that we're doing. Scientific ethics does not just depend on you not cheating on a paper or not falsifying data. It also comes with treating science with respect and anticipating the potential pitfalls as well as the potential advances rather than just going gung ho on a science because you can. You need to understand that we are part of the world, we are affecting the world, and any change in technology is also going to have a change in the way that we interact with this world.